let's start with a pretty simple example. Let's say we have a circuit, the switch is open, and in the circuit is a 10 volt battery, a 5 ohm resistor, and a 5 millihenry inductor. Let's ask the question, what is the battery current immediately after the switch has closed? So as soon as the switch closes, so we close our circuit. In a usual circuit, the current would start to flow immediately. So if there was no inductor, current would just flow around. But for this case, you close the switch, the current is initially 0. The inductor is going to oppose any increase in current. So immediately after, the inductor opposes the current flow. That means the current equals 0. Okay, so the inductor, right at the very beginning, it's going to oppose the current flow, which means that no current will flow at all in the very beginning. So it keeps resisting it, and eventually it will start to increase. So the current will flow. It's just going to take a little time because the inductor opposes that sudden jump in current. So it won't immediately jump up to some value. It's going to start at 0 and work its way up. Then the next question is, what is the battery current immediately after, the word immediately shouldn't be there. What is the battery current after the switch has been closed for a long time? So our switch is closed for a long time. We ask what happens in that case. Well, let's think about, after a long time, current equals constant. Because we know the change in current goes as an exponential, so eventually it does reach an approximately steady state. If the current is constant, it means that there's no change in current. If there's no change in current, then there's no potential across the ends of that inductor. And also, there's no resistance in our ideal inductor, so there's no potential across those ends due to its own internal resistance. So after a very long time, the potential across the inductor equals 0. What does that mean in terms of our circuit? It means that after a long time, there's no potential. That guy acts like a short circuit. So it means that our circuit really acts like this, as if the inductor is not there at all. And we definitely know how to find the current in this case. From Ohm's law, V equals IR. V is going to be the potential across the resistor, which is going to be the whole 10 volts. So our current I is going to be V over R, 10 volts over 5 ohms equals 2 amps. Okay, so that was a really simple example. Now let's do one that's similar but a little tiny bit more meat to it. Let's have a circuit that's got 2 resistors and an inductor, where these two are in a parallel branch with this one. So let's ask the question, what is the battery current immediately after the switch closes? Okay, so we're going to close that switch at t equals 0, and right away, what is the current? So for this guy now, the battery is able to pump out some current. So some current I starts to flow. The current hits a junction right here, and it has 2 possibilities. It can go this way, and it can go this way. In this branch, we have an inductor, and in this branch, when the switch is open, there's no current. When the switch is open, there's no current anywhere. So this branch starts with the current equals 0. When the switch closes, current would like to flow, but the inductor is going to oppose it. So for this branch, right after the switch is closed, I is going to be 0 because of the inductor. So the current flow will only happen in this branch. We can draw that if we wish. The current flow is going to come around this way, with none in this branch at all because of the inductor. And we can calculate that. So our circuit is a very simple one with a 10 volt battery and a 20 ohm resistor. V equals IR, so I equals V over R. V is 10 volts, R is 20 ohms. So our current is 0.5 amps. Okay, next, what is the battery current after the switch has been closed for a very long time? Now let's ask what's happening this time. So the switch has been closed for a long time. We've reached a steady state, so the current is whatever it's going to be. So current flows out of the battery, it hits a junction right here, it can come down through here, and it can come down through here. In this circuit, the current is going to be constant, so for our inductor, the potential across the two ends of the inductor are going to be equal to 0 again. It's equal to 0 because the inductor has no internal resistance and because the current is constant. So we can draw another circuit if we wish. So that means after a long time, our inductor just looks like a short circuit. I'm going to try and redraw that just a little bit smaller because I'm kind of out of room here. So now again, this is a pretty familiar circuit. I've got a 10-volt battery and two 20-ohm resistors in parallel. So we could find an equivalent circuit here. Clearly should have left more room. So our equivalent, 10 volts. Our equivalent is what we find when we do a parallel calculation of resistors. 1 over R equivalent is going to be 1 over 20 ohms plus 1 over 20 ohms. Gives us 2 over 20 ohms. So our equivalent resistance is 20 ohms divided by 2, or 10 ohms. So this equivalent resistance down here is a 10 ohm resistor. So then the current in this circuit is going to be the potential divided by the resistance. 10 volts over 10 ohms to get 1 amp. So our current starts at 0.5 amps and it gradually increases to 1 amp after a long time. So next we'll move on to a even a little bit more difficult example.